Hi, I'm Farhana and welcome to another lesson on trigonometry rules. Today we'll be focusing on proofs and applications of the three rules. Let's begin. Okay, so I'm sure you've always wondered, how is it that we know that the sine rule, the cos rule and the area rule are actually giving us the correct answers? So, how we know that these rules work is we first learn to prove the rules. Because we have a proof that the rules actually work for any triangle, then we know universally that these rules can be applied to any triangle. Let's begin with the first proof. We're going to start off with the proof of the area rule. Let's begin. So, look at our concept map. We've done all three rules already, and today we're focusing on the proofs and applications. Can you remember what the area rule was for any triangle ABC? So we had three versions. The first version was area equals half AB times sine of the angle C. Second one, half BC times sine of the angle A. And the third one, half AC sine of the angle B. And can you remember what order we needed the angles and the sides in? Or in other words, what pattern were we looking for? We were looking for side, angle, side. So basically, again, just to remind you, if we were using that one, we needed A, B, and C. So we're using that V pattern. Okay, so to begin the proof of the area rule, we have to construct H, which is the altitude of the triangle ABC. And specifically, we're going to draw this altitude from the vertex C. So what that means is we go to the drawing and we begin at C and we draw a perpendicular line from C down to our base. And can you remember? This should look quite familiar to you. We've done this lots of times. So that's going to be your height of your triangle, and this would now be the base of your triangle. Okay, and this little c would be the base. So, if you can remember from grade 8 and 9 geometry, how do we find the area of triangle ABC? Okay, so triangle ABC, it's half base times height. And what is our base in this case? Our base in this case is this line here, AB, or in other words, it's little c. Okay, and our height is the height we've constructed, which is this height. So, CH. So, if we were to find the area of triangle ABC, it will be half C times H. Now, looking at this triangle AC, and I'm going to label this piece here D. Looking at triangle ACD, we're going to try and find the sine of angle A. And what is sine of angle A? Sine of A is opposite over hypotenuse. So, let's write that down. Okay, so sine of A is opposite, and the opposite side to sine A was H. And the hypotenuse in this case was the hypotenuse for this triangle. So it was B. Okay, and rearranging this, we multiply both sides by B, so we end up with H is equal to B times sine of alpha. Okay, this is standard grade 10 trigonometry. Okay, now we're going to take this value for H and we're going to substitute it into this formula that we have written originally. So let's do that quickly. So we're going to have half C. Now instead of putting this H in, we're going to put in what we found for H here, which is B sine A. So it's going to be B sine A. And can you remember what we were trying to prove? We were trying to prove that the area of the triangle ABC is equal to half AB sine C. And if you look at what we have now, if we just rearrange this, it's going to be half BC, just to put it in alphabetical order, and something that looks familiar, half BC sine A. So, we've proved one case of the area rule, half AB the area of triangle ABC is half BC sine A. Okay, and similarly, we can prove the other parts of the sine rule. And can you remember what the other versions of the sine rule are? Of the area rule. So the other two that we can prove that it can be half AC sine B, and that can be the other area. And if we draw the height in a different place, we can then prove the third version, which says half AB, and we're using sine C here. Okay, so this area rule we did now, and the proof we did, was one particular proof using the height from the vertex C. If we moved around the height, then we can get the other two formulas that we've just shown you now. But if you notice carefully, the example that we've used now is an acute angle triangle. What happens if the triangle is obtuse? Let's quickly go through the proof. It doesn't change much except for one small tiny bit. Let's go through that quickly. Okay, so if the triangle was obtuse, then we draw the height as we usually would for the triangle there. And this would have been our angle A, so the adjacent angle would be 180 minus A. And how does our proof change for that? If you go through the steps for our proof, nothing changes much. Our area of our triangle ABC is still half the base times this height here. So half C times H. And now the one thing that does change a little bit is if we look at sine, we're looking at triangle ACD again as we did in the previous proof, but now in triangle ACD, our sine of this angle, we're going to be using this angle. So sine of 180 degrees minus A will equal to opposite over hypotenuse, so H over B. So sine of 180 minus A in our triangle ACD is equal to, it's equal to sine of 180 minus A is equal to opposite, and our opposite was H, and our hypotenuse in this triangle was B. And then we have to remember that because sine of 180 minus A from our trig rules, because this is second quadrant, is just equal to sine of A. So nothing changes from here onwards because now sine of 180 minus A, I can replace this with the sine of A, and we retain this H of B on this side. So what does it mean? It means that sine of A is equal to H over B. And when we rearrange this again, we end up with the same version of H that we had earlier, which is B times sine of A. And again, we're going to substitute that for this H that we had in our original formula for area. So again, exactly like we did earlier, H equals to B sine A. So we're going to put into here, we're going to put this for H, for this H that we had in this formula here, we're now going to put it in here. And so we end up with area of triangle ABC is equal to half CB sine A. And if we rearrange it in alphabetical order, it's just half B C sine of A. So you can see that the proof of the obtuse angle triangle is not much different. We just got to consider our angle being in the second quadrant, or 180 minus our original angle. Okay, we have to go for a short break. I'll see you after the break. Hi, welcome back. So before the break, we were talking about the proofs of the three trigonometry rules. We've already done the area rule, and now we're going to do the proofs of the sine rule and then the cosine rule. They're pretty simple, and we start off basically very similar to how we start off the area rule proof. Let's go. So, can you remember about what is the sine rule? Okay, the sine rule says sine A over A is equal to sine B over B equals to sine C over C. And the reciprocal version, A over sine A equals to B over sine B equals to C over sine C over sine C. So, we're going to start off with proving just one of them, and then the other we can deduce from our first proof. Okay, and can you remember when we use the sine rule? Just to try and recap quickly, we use the sine rule when we have one full pair of opposite sides and angles. Okay, so when we begin this construction, we're going to begin this construction exactly as we began the construction for the area rule. And that means we are going to be doing a construction, and we're going to construct h, the altitude, again from the same place that we did earlier, and we're going to construct it from vertex C again. So we take our pens and we draw a straight line from C down onto AB. Let's call this point D. And this is our height. Okay, so this is our height of our triangle. And we're going to now continue our proof. So once we've done that construction, that's the first step of our proof. Okay, now if we look at triangle ACD, which is this triangle here, ACD, this triangle here. If I try and write out a formula for sine of A, similar to earlier, it's going to be opposite over hypotenuse. So it's going to be H over B. And then we're just going to rearrange this to make H the subject of our formula, and we're going to end up with H is equal to B times sine A, because we've just multiplied throughout by the B. Right, now we're going to look at the other triangle, this triangle on this side, so BCD. So in triangle BCD, we're now going to make a formula, we're going to write out the value for B, sine of B. And sine of B is going to be, now that's the opposite, but in this triangle, this is going to be the hypotenuse. So sine of B will be H over A. So let's write that down quickly. It's going to be H over A. Now, we've got to just rearrange that again, just to make H the subject of our formula, and we're going to end up with H is equal to A sine B. Now, where are we going with this proof? So we've got two different equations that both equal to H. So what we can do now is equate both right-hand sides together. So we can equate B times sine A with A times sine B, because they're both equaling H. And we can now construct a new equation that looks like this. Okay, so B times sine A is equal to A times sine B. Pretty simple. We just found out sine of A, we found out sine of B, we made H the subject of the formula, and now we're equating both right-hand sides. The next part of our proof is really simple. Okay, so once we have this equation, okay, we're now going to divide both sides by AB. So I'm going to divide this side by AB, and I'm going to divide this side by AB. And what's going to happen now, can you see what's going to cancel out? Okay, so now on this side, the B's are going to cancel out, and on this side, the A's are going to cancel out, leaving us on the left-hand side with just sine A over A, and on the right-hand side, in the numerator, we're left with sine B over B. And that's exactly what we needed to prove. Sine A over A is equal to sine B over B. Right, so how do we prove the other way, other versions of it? We can just draw a different altitude, so we can just use the word similarly, and say similarly, if we do an altitude from B, we can do the exact same proof, and we can prove that sine A over A is equal to sine C over C. And if we drew the altitude from A, we can prove that sine B over B is equal to sine C over C. So basically what we've just done now is we've proved the entire sine rule. We've proved that sine A over A equals to sine B over B, and that's equal to sine C over C, so they all three have to be equal to each other. And remember, from this we can conclude the reciprocal version by just swapping that around. Okay, so that was the sine rule proof. Not too bad. Now we're going to do the cos rule proof, which works around the same lines that we just did the area and the sine rule proof. We actually start off in almost exactly the same way again. Let's begin. Okay, so what is the cosine rule? Remember, a squared plus b squared minus 2bc cos a. b squared equals a squared plus c squared minus 2ac cos b. And the last one, c squared equals a squared plus b squared minus 2ab cos of c. Okay, and again, exactly like we did before, we're going to start off with our construction. So let's construct our height again. We're constructing a height again from vertex C. So we're drawing our height perpendicular to our base. There's our base there. And our height, we're going to label it h. Okay. Right. Again, we're going to just start writing out a formula for sine of A. And sine of A will equal to, this is sine A, so opposite over hypotenuse. So it's h over b. And again, we're going to make h the subject of the formula by multiplying throughout by b. So h will equal to b sine of A. Right. Now we're going to do something slightly different because we want to introduce the cos. Because it's a cosine rule, we're going to find cos of A. So cos of A is now going to be in this triangle, because remember we're working with triangle ACD, it's going to be this side, adjacent, this side here, over the hypotenuse. So cos of A will be AD over our hypotenuse, which is B. Remember, in this case, we're working in triangle ACD. So we're working in this triangle. So in this triangle, if I want to find the cos of A, it's adjacent, that side, okay, which is AD, over my hypotenuse, which is B. Okay, now we're going to just rearrange this again, and we're going to make AD the subject of the formula. So AD will equal to B times cos A. We've just multiplied the previous line by B. Okay, but we have to realize something. If we're finding out BD, if I need to find an expression for BD, because this whole piece here is C, let me just grab another color. Because this whole piece here is C, if I wanted to write BD in terms of C, this little piece from here to here will basically be C minus AD. So I'm going to write BD as C minus AD. This will help us with our proof, as you'll see in just a minute. Okay, so we've got an expression for H, and we have an expression now for BD, and we have an expression for AD. Okay. Okay, so BD was equal to C minus AD. Let's continue. Okay, sorry, there was something that I forgot to write in here. Okay, sorry, so B was equal to C minus AD. But remember, we had this expression for AD, which we now needed to substitute in here. So BD was equal to C minus, and whatever we had for AD, I'm going to substitute in here. So instead of AD, I'm going to put this piece of the equation is here. So it's going to be C minus B cos A. Okay, so now we have an expression for BD that includes C and cos of A. Okay, so just to remind ourselves what we had on the previous slide, we had an expression for H, and we had just made an expression for BD. Okay, now if we look at this triangle here in BCD, so this triangle BCD, we're going to use Pythagoras. And if we use Pythagoras, we know that the hypotenuse squared, so A squared, must equal to this side squared, so BD squared, plus H squared. And that's just using theorem of Pythagoras, which we're quite comfortable with using for a while. Now, the reason we're using Pythagoras is because we want to, remember, we want to prove something about A squared is equal to B squared plus C squared minus 2BC cos A. Okay, so we're going to now substitute each of these. So for BD, we're going to substitute this in. And for this H here, we're going to substitute this in. Okay, so A squared is equal to C minus B cos of A. Okay, that's from here. And from H squared, we're going to say B times sine of A. Okay, now we just have to square these binomials. And if you remember our rules for squaring a binomial, let me just get rid of this extra mark we have here. Okay, now how do we square a binomial? We start off on this side. It will become C squared minus, if you multiply the 2 and double it, it's 2BC cos A. Our third term will be squaring this term here. So it will be plus B squared and cos squared A. And now we're going to square this one term here. It's a single term, so we just got to square it. So it will be B squared sine squared A. Right, now if you notice, we've got a B squared here and we've got a B squared here. So we're going to try and take out a common factor from these two terms. Okay, so here's it written slightly neater. A squared is equal to C squared minus 2BC cos A plus B squared. So we're going to take out B squared as a common factor. We'll be left with this cos squared A, okay, plus this piece here, which is sine squared A. Now, look at this middle piece in our bracket, and what do you notice about this? This reminds us of the identity that says cos squared plus sine squared equals 1. Okay, and we know the trigonometry identity from grade 10. So we substitute that for 1. And now we have something that looks almost exactly like what I want. So what did I want? A squared is equal to B squared plus C squared minus 2BC cos A. So what remains is just to rewrite this in the right order, putting that in front. And we end up with A squared is equal to, let's write that quickly, B squared plus C squared minus 2BC cos of A. So now we've proved the first version, and again, similarly, if we just change where we start drawing our height, we can prove the second version. B squared is equal to A squared plus C squared minus 2AC cos B. And similarly, if we move the height in from a different vertex again, we can then prove this third version, which is C squared equals A squared plus B squared minus 2AB cos C. And that concludes all three proofs now. Hi, welcome back. So before the air break, we were doing all the proofs of the three theorems, of the three rules, sine rule, area rule, and cos rule. Okay, so we're going to start off with doing some examples now with applications of all three rules. But specifically, today we're going to focus on those examples that require us to use variables. There's no numbers in it. There's variables. They haven't given us the values of the angles and the sides, but they've given us variables, and we need to write out formulas in terms of variables or the lengths of sides or angles in terms of certain variables. So let's begin. Okay, before we start, let's quickly revise how we decide which rule we're going to use. So we've done this a few times before. You should be very familiar with this. So the first thing we look at is the triangle right angled? If it is, then we ask, does it have angles? If it does have angles, then we go to grade 10 trigonometry using the three ratios, sine, cos, and tan. If it doesn't involve angles and it's a right angle triangle, then we probably have to use theorem of Pythagoras to find the sides. And the grade 11 part is if the triangle is not right angle, the first question we ask, do we have one full pair of angles and a matching, one full pair, that means an angle and its opposite side, so are we given that? And if we're given that, then that means use the sine rule. And remember again, the sine rule is used when we have angle, angle, side, or side, side, angle, but not an included angle. Okay, but if we don't have one full pair of angles and sides, then we know we're probably going to be using the cosine rule. And the cosine rule, if you want another way to remember when to use it, we use it when we have side, angle, side, or when we have three sides and we want to find an angle. Remember here we're kind of looking for a V pattern. Okay, so let's begin with our first example. Okay, in this figure they've given us a triangle XYZ with y is equal to theta, so they've given us this angle here, and they've given us these two sides xy and yz which are equal, and they both equal to b. Okay, and they want us to show that xz is equal to some expression, this expression here. Okay, so what we have to look at again, we've got to check our rules. Is it right angled? No, it's not right angled. Do we have one full pair? As it stands, we don't have a full pair. We definitely don't have an angle and a matching side. But what we do have, which means we're probably going to use the cos rule. So let's check to see if we have exactly what we need for the cos rule. So remember, when we're looking for the cos rule, we need to have a side, angle, side. So do we have a side, an included angle, and another side? Yes, we do. So we've checked all three boxes for our cos rule. So where are we going to begin? We're going to start off by writing out an expression for xz, because that's what they want us to do. And we know if we use the cos rule, if we're finding an expression for xz, then we can use the v across from it. So we can use this side, the angle in between, which is that one, and the side adjacent to that angle to find the value of xz. So let's begin by writing that expression. Okay, so we decided that we don't have one full pair, okay, just to double check where we started off. So in other words, we can now write an expression for xz. So xz squared will equal to that side squared, so it's b squared, okay, plus the other side, so it's going to be another b squared from that way, okay, minus 2 that side, so it's going to be b, and we're going to say cos of the angle across from xz, and the angle across from xz is theta. Okay, so basically we're saying xz squared is equal to xy squared plus yz squared minus 2 times xy times yz times cos of the angle in between, which is theta. Okay, so that's what we had written on the previous slide. This is just a neater version. So now we're just going to do some algebra to kind of neaten this up and see where we end up. Remember, we're looking to find xz. What we have on the board at the moment is xz squared. So we begin by just adding b squared plus b squared to give us 2b squared. We multiply out these 2b and we end up with another b squared. And now you'll notice we can see what? It's quite obvious to see there's going to be a common factor. Our common factor, we've got a 2b squared here, and we've got a 2b squared here, so we're going to factor out the 2b squared. Okay, so what will be left with here? From the first term, we're going to be left with 1 minus, and from the second term, we've taken out the 2b squared, we're just going to be left with cos of theta. Let me just get rid of this. Okay. Now, remember, we're not looking for xz squared. We are looking for xz. So we have to find the square root of this whole right-hand side. So let's find the square root of the right-hand side. Okay, so if we find the square root of the right-hand side, we're going to put everything under the square root. So it will be 2b squared into 1 minus cos of theta. Now, if you look at this expression, I could take this b squared out of the square root, and what will I be left with? It will come out of the square root, and then the square root of b squared is simply b. So if I just write that out now, I'm going to end up with that b coming out here, and I'm going to be left with 2 and the bracket, which is 1 minus cos of theta. Let's go back and see what they asked us to prove. They wanted us to prove this. They wanted us to prove that xz is equal to b square root 2 brackets 1 minus cos theta, and that's exactly what we've proved. Okay, so it does get a little tricky when there's variables instead of numbers or lengths of angles, lengths of sides at angles. But eventually, if you apply the rules in the order that we do, it'll make it a bit more easier for you to decide which rule you need to apply. Let's try another example. Okay, so George says that the point G, a distance from the vertical office tower at AT, and he sees Nandi at the window at n meters from the top of the building, so that's that height. And the angle of elevation from George to A is alpha, so this big angle here is alpha, that one's alpha. And the angle of elevation from George to Nandi is beta, which is that angle there. Okay, and they ask us to express G1 in terms of alpha and beta, and then they ask us to express A in terms of alpha and or beta. Okay, let's go and examine this diagram quickly. Okay, so they want us to find G1, this angle here, this small piece here. Now, the whole angle here is alpha, okay, and this little piece is beta. So obviously, G1 is simply what? It's simply alpha minus beta. And the next question they asked us is to find A. Now, A is in this big triangle here. It's part of the triangle AGT. And in this triangle, we've got A, we have this 90-degree angle, and this angle here, we know is alpha. So, what will A just be? So, because this angle is 90, it means the two remaining angles have to be 90. So, in other words, because alpha plus A had to equal to 90, that means A just had to equal to what? 90 degrees minus alpha. Okay, and how do we know that from three angles of a triangle? Because we already have this 90, and we have alpha here, so A had to be the complement of alpha, which was 90 minus alpha. Okay, we're going to use these two in the next part of our question. Now they ask us something a bit more complicated. They ask us to show that H is equal to n cos alpha sine beta over sine alpha minus beta. Sounds quite complicated, but we know we just need to find an expression for H. Okay, so H belongs to this small triangle here. But if we look at the amount of information that we have on this triangle here, we've got beta and we've got H. So it's easy. It's a right angle triangle. We only need 2 bits of information, and we have them. We've got H and we've got beta, so we can rewrite an expression. We can try and find an expression for sine of beta, and sine of beta will be opposite over hypotenuse. So it's going to be H, and the hypotenuse in that case was Gn. Now, we're going to rearrange that. So we make H the subject of the formula, just multiply throughout by Gn. So we're going to get H is equal to Gn times sine of beta. Right. Now we're going to be using sine rule in triangle AGN. So in triangle AGN, we already know that Gn, okay, we're going to use sine rule. So we're going to use Gn and the angle across it. And can you remember earlier we said this angle was 90 minus alpha. So in other words, Gn over the sine of the angle across it, so sine of 90 minus alpha, is equal to, and we're going to use the other side that we have, and the other side that we have an expression for is going to be an, or it's going to be this across and the angle across it. So it's going to be n and sine of the angle across it. And across from n, we had G1. And remember, what was the sine of G1? I mean, what was we found G1 to be earlier? G1 was, can you remember? It was that big angle minus the small angle. This is what G1 was. Okay, so we're going to substitute that in here. So we're going to say alpha minus beta. So we've used the sine rule again in this one here. Let me just remind you what we've done. We've said in this triangle AGN, Gn over sine of A is equal to An, which is little n, all over sine of G1. And that's the expression that we have here. Okay, so there's a neater version of what we had earlier. Now, we're going to, we have two choices. We can either multiply throughout by sine of 90 minus theta, but what do you notice about sine of 90 minus theta? What does it remind you of? Can you remember? When we did reduction formula, then sine of 90 minus alpha, we got to use the Coco rule, so it becomes cosine, oh sorry, my pen is doing funky things. Okay, it becomes cosine of alpha, okay? And that's from using the reduction rules. I'm not sure if that's how you learned it. A lot of people refer to it as the Coco rule because you find the co-ratio of the complement. So sine of 90 minus theta becomes, sine of 90 minus alpha becomes cos of alpha. Okay, so what I've done first is I've just multiplied first through by sine of 90 minus alpha just to get rid of the denominator on the left-hand side. And now I'm going to change that 90 minus alpha into cos of alpha. Okay, now we have an expression for Gn. So now we have an expression for Gn. Okay, but remember we were trying to find an expression for H. And earlier we said that H is equal to Gn times sine of beta. Okay, sorry, there was just some things I needed to get rid of. Okay, so H is equal to Gn sine beta. And now I'm going to substitute this piece here for Gn. Okay, so I'm going to put that in place of that Gn, and let's see what happens. Okay, so n cos, sorry, it was actually that expression, the simplified version. N cos of alpha over sine of alpha minus beta. Now I'm just going to take this and just neaten this up and multiply this into the numerator here. So we end up with that expression, and that's exactly what they asked us to prove at the beginning. They wanted us to prove that H is equal to n cos alpha sine beta over sine of alpha minus beta. Okay, that brings us to the end of that example. We take a short break. I'll see you after the break. Hi, welcome back. So before the break, we were doing application of the three trigonometry rules. Specifically, we were looking at examples with variables. We continue with that now. Okay, in this example, they've asked us to find the area of the shaded region in terms of x, alpha, beta, phi, and theta. So what we have to first look at the diagram and try and examine all three triangles and see which one has what kind of information that we can use. Our first triangle is triangle ABE, and triangle ABE is a right angled triangle, and we have 2 bits of information, which means it's solvable. Okay, triangle BCD has 3 bits of information. We've got an angle, and a side. And look at this. We have one full pair because we have B and we have the side, we have beta and we have the side across it. So we can probably use sine rule if we are using that triangle. The third triangle we have is this shaded triangle, and that's what they want us to find the area of. But in this triangle, we only have at the moment 1 bit of information. All we're given is theta. So we need to find at least 2 more pieces of information before we can find the area of the triangle. And it seems like we need to use this triangle and this triangle to try and find the sides of our shaded triangle. So what we're going to do is we're going to try and find, let me just grab my pen quickly. Okay, we're going to try and find this side, BE, using this triangle. And then we're going to try and find an expression for BD using this triangle. And then see if we can find the angle in between. So if you look at this angle in between, in the shaded triangle, we could use this angle and the exterior angle to find an expression for that. So we kind of have a plan, we have an idea of what we're going to do. So we're going to find BE, then we're going to find BD, and then we're going to find an expression for that angle. So let's begin. Let me just clear up some of these funny marks they've had to enter up on the screen. Okay. Okay, so we're going to start off with triangle ABD, and we're going to start off with, because we have the adjacent and the hypotenuse, we're going to end up using cos, because cos of phi will be x over this length here, which is BE. So cos of phi will equal to the adjacent side, and adjacent to phi is x, and the length of the side, the hypotenuse, is BE. So remember we said we're going to find an expression for BE. And now if we rearrange this and we multiply throughout by BE, we can just end up with BE equals to x over cos of phi. So now we have an expression for that side. We're going to do the same thing now and use this triangle to find an expression for BD. Okay, so in triangle BDC, remember we already decided we have one full pair. Okay, so we can find BD using sine of the angle across it. So BD over sine of alpha, and then on the right hand side we're going to use our full pair. And what was our full pair? That was the side, so x, and the angle across it was beta. Okay, and then when we rearrange this, we're going to multiply throughout by sine of alpha, and we end up with BD equals x sine alpha over sine beta. Now we have an expression for BE and for BD. So there's the two expressions we found in the previous two slides. BE is equal to x over cos of phi, and BD is equal to sine of alpha over sine of beta. What remains now to find, so we've got an expression for that side, and remember we need side, angle, side to use the area rule. We need to find an expression for this angle. And we said we can use exterior angle of a triangle, so triangle angle DBE will simply be the exterior angle, which is beta minus theta. Okay, so we have this angle here, and we've got side. So area will be, so we're going to now write an expression for the area of our triangle. And remember, we find the area of the triangle, it's going to be half BE times BD all over sine of the angle in between. Because remember again, for area rule, we're looking for that V pattern. Okay, now we're going to substitute these expressions for BE and that expressions for BD, and we're going to end up with that. So I've basically just put this exactly as it's in here for BE and exactly as we found for BD. Now we're just going to clean up some of the algebra and see what we end up with. And because we're multiplying x by x, we end up with an x squared. So we got x times sine of alpha, and this belongs to our numerator. It goes up there. And at the bottom, we got 2 cos phi over sine of beta. So does that answer our question? Did we find an expression for the area of BED in terms of all our variables? Yes, we did. Okay, so our next question. In this figure, we've got P equals to A, Q2 is equal to B, and PQ is equal to H. Okay, and they want us to find, they're telling you PQ and SR are perpendicular to RQ, so they give us that this is 90, and they want us to find expressions for SQ and RS. So SQ is in this triangle, and it's pretty simple, okay? SQ belongs to this triangle. In this triangle, we've got 3 bits of information, and if you look carefully, we've got 2 angles, we've got no full pair. But we know we can find S1 because we have the other 2 angles, we can find S1 in terms of A and B. So that's where we'll begin. Because once we found S1, then we will have one full pair in terms of S1 and H. And we can use Sine Rule with that other pair as well. Okay, so S1 is equal to 180 minus A plus B. That's just using 3 angles of a triangle. Okay, so now using the sine rule, we can say that SQ over sine of the angle across it. So across from SQ we have A, and H, that one, and the sine of the angle across it, which was sine of S1. And S1, we had this expression, which was 180 degrees minus A plus B. Okay, let's continue. Right, so that's what we had written on our last slide. Now remember, what does this remind you of? Sine of 180 minus reminds you of second quadrant. And remember that we have, if we know that sine of 180 minus sine of 180 minus alpha equals to just sine of alpha. So we're going to use that rule to simplify this. And so we're going to end up with SQ over sine A is equal to sine of, it'll just become A plus B. Okay, rearranging this, we multiply throughout by sine A, and it ends up in our numerator on that side. So we've answered the first part of our question, which is SQ. Now we're going to find an expression for RS, and we're going to be using this triangle to find an expression for RS. Okay, so remember we've got something for SQ already. Okay, so but we need to find an expression for Q1. So because this is B and this is 90, Q1 will simply be 90 degrees minus B. Okay, because both angles are 90 and that's B, so Q1 is a complement of B. Okay, so sine of Q1 is going to be opposite over hypotenuse, and the hypotenuse in this case is QS. And remember, QS or SQ is what we found earlier. And we're going to just plonk that expression in for QS earlier. And what did we find QS to be earlier? Earlier we found QS or SQ to be that. That was our previous slide. We had that answer. And sine of Q1, and Q1, remember, we found it to be 90 minus B. So I'm going to put in here 90 minus B. Now remember again, sine of 90 minus B reminds us of what? Sine of 90 minus B reminds us of the Coco rule again. So it becomes the co-ratio, which is cos of the complement, so B. Okay? So we're going to change this sine of 90 minus B into cos of B. Okay? And cos of B will now equal to this. Sorry, let me just erase my writing. Give me a second. Okay, so we're going to end up with, okay, so we've changed that sine of 90 minus B into cos of B, okay? And now we're just going to rearrange this because remember we needed to find for RS. So I'm going to multiply cos of B by this denominator here in the next step. And once I've done that, it's cos of B times H sine A over sine alpha A plus beta. And I've just got to just neaten up the algebra here. And there we go. We now have an expression for RS, which involves all our variables as they expected. So RS is equal to H sine A cos B all over sine of alpha plus beta. Okay, so that brings us to the end of this session. I hope you enjoyed it because the next session we're going to be doing examination type questions. Till then, bye.